In an algebra class, you'll learn that the logarithmic function is the inverse of an exponential function. While this is true, the creation of the concept named logarithm came about without thinking of exponents at all. In the early 1600s, the mathematician John Napier used the Greek words logos and arithmos to name his concept with a word that means ratio number. His motivation for the idea of a logarithm was to simplify multiplication, division, and roots to operations like addition, subtraction, and divisions by 2, so that calculations involved in astronomy, which use very large numbers, could become easier. This had precedence in astronomy, which used trigonometry for a lot of calculations where there are formulas to simplify multiplication to addition, like 2 cosine A cosine B equal to cosine A minus B plus cosine A plus B. There also were trigonometric tables to look up values to use with this formula. So Napier calculated 90 pages of tables of logarithms which could be used in heavy calculations along with the well-known identity. Log of xy to the base b is equal to log of x to the base b plus log of y to the base b. These tables led to the invention of the slide rule to carry out some of the calculations, and the slide rule was used widely up until the 1970s when the pocket calculator was invented. It is on the slide rule that we find a logarithmic scale, which is a way to display a large range of numbers in a small amount of space, and this leads us to the piano. There are 88 keys on a piano, starting with an A on the left, ending with a C on the right, and middle C, well, right in the middle. Each of these keys have a letter name and pitch associated with them, but let's just focus on the octaves of A for now. If we start with the A on the lower left, we'll call it A0. An octave to the right of this is another A, which we'll call A1, and this continues for a total of 7 A's above the one we started with. The frequencies, measured in hertz for these A's in the equal-tempered tuning scale, are as follows. A0 is 27.5 hertz, A1 is 55 hertz, A2 is 110 hertz, A3 is 220 hertz, A4 is 440 hertz, A5 is 880 hertz, A6 is 1760 hertz, and A7 is 3520 hertz. If we even just consider the table we have here, we are looking at a logarithmic scale. Here's why. The difference in frequencies start to get larger as we read from left to right, but the physical distance between the cells in the table stay the same. The difference between A0 and A1 is 27.5 hertz, whereas the difference between A6 and A7 is 1760 hertz. The large range of numbers from 1760 to 3520 is the same small amount of space as the range between 27.5 and 55. Furthermore, we can notice the connection to the exponential function with these numbers, since we can go from any A to another A by just multiplying by a power of 2. As another way to visualize this logarithmic scale, let's look at a traditional number line with these numbers plotted. Notice how the numbers are really bunched together on the left, but then they get much farther apart as we move to the right. But if we use the piano keyboard as our number line, all of the A's are the same physical distance apart, and this is true for any other note and their octaves. This allows for a much easier way to play the piano. On this piano number line, we can also see how the powers of 2 relate. If we use F to stand for the fundamental frequency of A0 equal to 27.5 hertz, then the rest of the frequencies come from just multiplying by successive powers of 2. To see how the ratio number meaning of the word logarithm comes into play, there is a simple relation between the number of octaves between two frequencies. If the two frequencies are labeled F1 and F2, then the number of octaves between them is equal to log of F2 divided by F1 to the base 2. So for example, if F1 is A0, which is equal to F times 2 to the 0, and if F2 is equal to A4, which is equal to F times 2 to the 4, then the number of octaves is equal to log of F times 2 to the 4 divided by F times 2 to the 0 to the base 2, which is equal to log of 2 to the 4th to the base 2, which is equal to 4. And we can see from our chart that there are 4 octaves between A0 and A4. There is another logarithmic scale that is related to music, and that is sound intensity level, which is measured in decibels. To understand why a logarithmic scale is useful, we'll start with some facts. First, the lower limit of audible intensity, this is the threshold of hearing, is 10 to the negative 12 watts per square meter. The upper limit of audible intensity, this is the limit of pain, is 1 watt per square meter. The range of values from not being able to hear something to a sound being painful is 1 trillion. That's a wide range, so a logarithmic scale makes it easier to convey. Similar to the relation we had for octaves, we have the following for sound intensity level. Intensity level is equal to 10 times log of I divided by I0 to the base 10 measured in decibels. where I sub 0 equal to 10 to the negative 12 watts per square meter is the reference intensity. This means the upper limit of hearing has an intensity level of 10 times log of 1 divided by 10 to the negative 12 to the base 10, which is equal to 10 times log of 10 to the 12th to the base 10, which is equal to 10 times 12, or 120 decibels. For a frame of reference, a typical loud concert is 120 decibels. A motorcycle engine is 95 decibels, normal conversation is 60 decibels, and a whisper is 30 decibels. But it is important to remember that addition in the logarithmic scale relates to multiplication in intensity. This means that every time you add 10 decibels, you multiply the audible intensity by a factor of 10. Since 30 plus 90 is equal to 120, this means that a typical loud concert is 10 to the 9th, which is equal to 1 billion times as loud as a whisper. This also demonstrates for us how the logarithm can tell us the power of the exponent. In that previous example comparing a whisper to a loud concert, the difference in intensity level was 90 decibels, which means 90 is equal to 10 times 9, which is equal to 10 times log of 10 to the 9th to the base 10, which is equal to 10 times log of 1 billion to the base 10. Hiding in there is an answer to the question, what does this notation, log of 1 billion to the base 10, even mean? What it represents is a power. So if we write power equal to log of 1 billion to the base 10, then we can write the related exponential equation. 10 to the power is equal to 1 billion, and we know that that power has to be 9. What we have seen in these examples is how logarithms relate to ratios of numbers and how logarithms relate to exponential functions. Our calculations are much easier now with calculators, but it's important not to miss why logarithmic scales are a useful way to convey information.